So as numbers are just starting to kind of stabilize, I'll give a quick intro and then we'll hand over to our speaker. So today we are very excited to have Dr. Mohammed Afar with us. I'll give you a very brief intro of him and then he'll be able to introduce himself if I've missed anything, but he has his PhD in Earth Science from the University of Iceland in Reykjavik, his Masters in Earth Observation from the University of Twente, and then did some postdoctoral work at the University of Twente as well, and is now currently an assistant professor with the Department of Geosciences, based in the College of Science at the University of the Arab Emirates. His research includes the likes of remote sensing, image processing, GIS, things like thermal remote sensing, volcanic hazards, big data, and environmental analytics for monitoring and hazards. So he does a bit of everything. So we're very happy to have you here for COMET. Just a reminder as well, we have our annual meeting upcoming in a couple of weeks' time. So we hope to see a lot of you there. But for now, I will hand you over to Dr. Mohammed.
Thank you very much for the introduction, Erin, and thank you very much for inviting me for this nice webinar. So I would like to give some of the insight for the, like you see in the titles, about the time series and remote sensing, especially for geological hazards. So, but to be specific, I will explain more about landslides here, although time series is using for any type of hazards, but in these seminars, I will only use the landslide as the examples. So here, a bit of background. For, as you can see, if we talk about the change in the land surface, it means these are marked by the shift in time series patterns. You can see as the times goes, sometimes there's a gradual change from high to low, or to low high, and you have abrupt change that's suddenly changing, or you can have an abrupt change and then follow up with the recovery. And then you have a harmonic model, which is, this is mostly like in the seasonal patterns. You have a, for example, if this is temperature, you have summer, winter, temperature, summer. And then that's mostly the time series tell you about. So you can change, you can see the change from the patterns, basically. So in the remote sensing, usually, if we want to do the change detection, for example, from 2010 to 2020, we use kind of only two single points of these times, like let's say only 2010, 2020. So this is kind of inadequate measurements, basically. So how to make it adequate? Basically, as much or as dense as possible of the data sets we collect, and then it can tell you a story what happens in the between, for example, between or after, right after 2011 or right before something happened. So if we can manage to do these things, so basically we can tell a story about the time series. So as you know, change happens, right? Any times a change happens. For example, I will just show you examples of me. This is in 1992, just a little baby, basically. And then in 1997, yeah, it's just growing up. And 2013 and 2017, basically, you can see the change from, like, this is 25 years, let's say. And of course, now it's 2026 is completely changed again. But in here's what I want to show you. That's, you know, the change is not suddenly happen. Sometimes it's just like gradually change. But commonly in hazards, we have a sudden change that can completely make this land surface kind of difference. But in here, I will not talk about myself, but the key points of these presentations, I will talk about remote sensing, especially for the dense time series, for analysis of all available images over times. And in this case, we use the 2 decades of Landsat satellite Earth observations, which is now it's freely available in the cloud or geospatial cloud computing platforms such as Google Earth engines, and you can have also the planetary web and then Amazon Web Service. Basically, you can find this kind of data sets. And this kind of open up new opportunities for rapid and automatic landslide mapping. So we can get mapping in both timing and also the locations of the landslides. So from here, we can have an insight into a landscape or pattern that indicating the surface change basically. So a bit of background about this. So it defines basically 3 stages of landslide detection that we commonly found in the most papers or in manuscripts. We have level 1 detections, level 2, and level 3. Let's talk about first two, level 2 and level 3. So level 2 and level 3, basically, this technique mostly uses advanced deep learning or object-based to map landslide inventories. Mostly this is delineate the landslide as much as possible. So the aim of this level 2 is for complete inventories and precise spatial delineations of some of the event-based landslide. Usually they use the very high resolution satellite image or UAV or drone. They use mostly that things. And in level 3, usually this is also aimed for validations and stored into inventory database. And mostly this is using manual delineation. So geologists usually like to do delineations of landslides here to be precise as possible. So now what about level 1? So this is kind of an explorer phase. So in level 1, basically I will go to the aim first. The aim for this stage is to detect where are the change or where are the change pixels and when was that happens. So if you see, this is same landslides. It's not really as precise as the one that's below, but overall gives you trend or it gives you spatial patterns. Where is the landslide? And then the most important thing, when also. It can show you when some of the landslide happens and then overview of the area that impacted by landslides. And this one is using the medium or freely available data sets like a Landsat, or even we can use Sentinels in the end. Now the question is how to apply this kind of level 1 concept to landslides. So we can go first to the basics of the remote sensing. We do the pixel level analysis. So sometimes we are really interested in one pixels, although in the reality we process all the data sets of whole images. But now we go first to pixel level analysis. So let's say we're back here to pixel level analysis. We have time and the x-axis, and then in the y-axis we have surface reflectance. It can be NDVI or any indices or band, anything that we can use. So this is in the pixel level. So if you, for example, if you click one pixels like this in 1990, then the same pixels in 2010, you can see this is kind of similar. So it's no change in pixels. But that's from 2 clear observations. What about if we increase 3 clear observations, like a growing seasons in 1990, 2000, and also 2010? As you can see, it's kind of not much difference, right, for the 3 years. And then let's say we increase multiple clear growing seasons from 1984 and 2000 until 2010, we can see a bit of difference. So maybe this is the peak, and then a little bit lower here, up, down, up, down. So it can tell you something. So this pixel is changing, but it's not as much. And then we increase for multiple clear growing season and off seasons observations. Now we have some of the data sets, so we can see something happens here. Maybe you can have a seasonal patterns like a up, down, like a harmonic models. We can use harmonic models here. And then if we put everything here, so all the data sets, so this one that show you from 1 pixels from 1984 to 2012 or 2010. So these are the data sets. So from the single pixels. So now the questions is what this pixel tell you about that and how to make it interpretable. Let's say now we use harmonic model from the continuous change detections and classification. So this is kind of a decade ago, the models CCDC invented by Zhu and Woodwalk in 2014. So this is the aim for this model previously for the change detections. So not only landslides, it means deforestation, urban can be used, but in this case, we will use for the landslides. So in here, the terms of continuous, it's referred to the ability to detect a change at any given time within the observations period, let's say from 1984 to 2012. So it will give you insight of this change. Let's say now, what is this CCDC? Basically, if we want to be simplified, this is kind of time segmentations. In remote sensing, we now have a object-based segmentations. It's basically for the image, you can have a segment in the image based on the object. But in here, it's more to temporal segmentations or time segmentations. So we segment each time, for example, this, we have segment 1, that's clearly there's no change, only change in the seasonal patterns. But around 2002, there's a shifting in the seasonal patterns. Maybe the vegetation is getting lesser or something happened with these vegetations, a lot of stress. So that's the signals and the surface reflectance kind of weaker than the previous one. So this is the segment number 2. So from this concept, basically, we can have models of, for example, if we can segment each time, we can reveal some things behind this time. Let's say this is from single pixels to temporal. Basically, if you have one single pixels here, so this is in Nepal, landslides in Nepal 2015. If we reveal the pixels here, one single pixels, it shows you it's the data from last 30 years. It shows you that there are at least 3 changes. For example, this vegetation is kind of low vegetations, but in close to the 2000s, the vegetation is higher, but in 2015, this pixel just slightly abrupt change. So this is because of landslides. Basically, each pixel has a story to tell you, and these temporal segmentations allow us to summarize what's the story behind each pixels. So again, so in the examples, like if you see the pixel number 1, it shows you there's only 2 segments. So this first segment is the vegetation. So if you see in the y-axis is NDVI, and then x-axis is the time. So as you can see, it's quite stable until in 2018, it was dropped and then changed to another segment in 2018. Let's see the pixel number 2. There's no change. Basically, this is only one segment of vegetation state. So these pixels, there's no change in the last 2 decades. And then pixel number 3, you can see there are three segments. We have a segments of high vegetations maybe, and then lower vegetations, and then even lower vegetations in the segment number 3 and start in 2010. So we can tell, I can tell you something happened in this area. For example, maybe there's an anthropogenic events in this area. So this, from the single pixels, it can tell you something happened. So now, from these temporal things, we can tell you, well, this one is disturbing because of disturbance because of the landslide, let's say, because the high vegetation suddenly changed into low vegetations. So from this temporal, we can map this back into the spatials. It's like this. So each pixel show you the date of the change. So like in here, the orange, maybe this is around 2015, and then the blue, this change around 2010 or 2011. And each color it show you change that related to the years or related to NDVI drops. But however, here, not all disturbance that related to NDVI drops is due to the landslides, right? Maybe like, for example, I give you again example here. This is related to anthropogenic events. So, and then now, how to minimize to detect some things that not related to the landslides. That's why also we introduced the knowledge-based filterings. So in here, we filter the areas that are unlikely to have landslides. So let's say we just get rid of the water bodies and then get rid of the slopes that more than 10 or 15 degrees or less. So by putting all the filters there, we can just isolate the possible pixels that only related to landslide, although it's not perfect, you know, that's kind of filtering. There's no perfect filtering, but at least we can isolate based on this knowledge base. So now, after we have this cumulative disturbance map, we also can have a time series of the numbers of pixels that detected as change. So from here, we can see which years that have a number of pixels change. Let's say this is in Naples. In Naples, especially in this area, it's commonly to have a landslides, especially after the Gorka earthquake. Also in 2015, you have this is the higher numbers of the change. Now, we move to the study areas. Currently, we tested in the total 5 areas, like in the Iburi, Japan, and Kashmir, and Pasang Lamu, and Karnataka, and also in Porgera. So we basically test these things to see whether this method is transferable or not. So the things that you need to note, we don't change any parameters. So in here, we want to test the default parameters that we use. Same, like for example, in Iburi, we use same parameters like in the Kashmir, Karnataka, Porgera, and Pasang Lamu to test the transferability. Is it this method can be used or not for different kind of areas? So this one is the disturbance patterns in Iburi, Hokkaido. As you can see, this is the detected, I can zoom it first, maybe you cannot see clearly. So the reds, it shows you the date of the landslide. It means around 2018. And then the blue here, maybe this is around 2010. So, and then the inventories, the black things, this is the inventories from the reference. So from the reference, as you can see, it's quite matched with the results from the CCDC. And also you can see on the right chart here, so this is number of pixels that detected as a change. So as you can see in 2018, this is the February earthquakes. So suddenly we have a spike in the change in the pixels, basically. So when we move to other areas, so this is in Kashmir. And Kashmir is also similar. You have a patterns, disturbance patterns, and then this blue things is from 2005, changed in 2005. As you can see also in 2005, we have 2005 Kashmir earthquake, which is quite big earthquake at that time. So here, you expect to have a high disturbance, and then the results you have quite large of landslides happen in these areas. And then also in this area, it's detected another spike, at least these 3 spikes, huge spikes. But this is when we carefully examine, this thing is not related to the landslide, but this is related to deforestation due to the relocations of the new city of Balakot, because they moved to the new city of Balakot in 2005 because of this earthquake. They tried to build the new city, so that's a lot of deforestations in these years after the earthquake. And then also in the Karnataka, India, we have disturbance patterns, which is like this, if you can see. And also the pixel change detected around 2018, which is have a huge spike here. And after that, we go to Porgera, which is Papua New Guinea. So we have also the patterns, which is this is quite low change, although the area is quite active. So you have you expect small landslide happen or small disturbance happen, but in 2018, after the Porgera earthquake, there's a spike in the change. So this is clearly, you can see from these disturbance patterns from the time series, what happened with the pixels. So these maps can tell you the change for each year, or even the specific dates. And this is for example in Pasang Lampung, so same. You can see quite a lot of spike in this area, but it's more clear after 2015. You have a huge spike after that. Now, how to assess that is landslides or not, or only pattern of disturbance? So if you see, so we dealing with the medium spatial resolution data, which is if we go to head with the reference data sets, let's say this is our results, like a pixelated, of course, we are dealing with the pixel base. And let's say the inventories, it's like this. Okay. The inventories is really detailed because it's man-made, or this is manual delineations. Of course, for geologists, they really like to draw it. It's clear boundaries. But as you can see, for the overall, the locations of the landslides, it's fine. But for the shape is not really say you something. This is if you assess the accuracy, maybe it's lower accuracy, it can be 50% accuracy or 60% accuracy, but that's not our aim. So that's why we don't want to have a head-to-head accuracy or comparisons like apple to orange comparisons. So we want to have this as fair as possible, the comparison. So we use slope unit approach. Basically, this is create you the density maps of the landslide for each of the slope. So we put our results and also the inventory result to see whether this is belong to some of the slope unit. And here we just make a comparisons of our proposed method and also the reference method or reference inventories to see the pattern, spatial distributions of these landslides and also the densities of the landslide. Then we do the regressions to see whether our method and also the reference match in the area. So this is for the Ivory, we got 0.81. And this is for Kashmir, we got 0.85. And for the Karnataka, it's quite lower, it's 0.62. So our methods kind of detecting denser rather than in the reference inventories, especially in this area. And then some areas also missing here. This is due to the persistent cloud cover in this area. So as I mentioned before, that we are dealing with the optical data sets. You know, the optical is really not good for the cloud cover. So might be missing something here. And then for the Papua New Guinea, it's even lower, it's 0.56. But if you can see in the spatial distributions, it's quite, I will say visually, it's quite similar distributions of the landslides. Since this area is really big, so in here, basically, we failed to detect the landslide that associated with the rainfalls in here, because at the times the cloud cover again will make this method suffers, especially for the areas that have a lot of cloud. It's similar like in the Karnataka. So now for other works, we also work with other temporal segmentations methods, not only CCDCs. And we have used the more simple one like a LandTrendr. So we do the same things if these methods quite accurate or not to delineate the landslides. And even for the LandTrendr, we try now to work to see whether some of the landslide have a recovery. For example, this is the one in Lombok 2018. Now in 2022, we've seen some recovery. So when you see these pixels, basically this recovery is not naturals, but this is more to the human interference. So they kind of put forestations. They would just make it back to the forest side. So it is these areas basically. So also now we are ongoing works to do the web apps for the global landslide finders. Basically, this is in preparations app to see whether we can make these applications work for the globally. And if you go to certain areas, you can just start load first change or load last change, and then it will pop up the results of the landslide in the pixel levels, basically. So now we go to the potential future works. So in the futures, maybe we need to not depend only on NDVI as indicators, because in NDVI you only solely use vegetations as your index. But what happens if our landslide happen in the arid region or semi-arid regions? So we need to explore other indices, because not all landslide happen in the highly vegetated area. And then might be we can explore also other methods for the temporal segmentations and also the potential machine learning integrations, especially that dealing with the time series. And the data sets, now we have a harmonized both Landsat and Sentinel-2, right? So if the denser is our data, the better is our results. So previously, the example that I gave to you, it's from the Landsat. Landsat is every 16 days, although we use all the data sets every 16 days since 1984. But if we can use this harmonized with Landsat and Sentinel-2, maybe we can have a denser time series. And then potentially also we can use PlanetScope with a very high temporal, every 1 day, and also very high spatial resolutions. And also might be we can think about to use radar data, for example, in GRD data in backscattering, because the advantage of radar, it's less effect of clouds. However, the temporal patterns need to be carefully assessed for these things. And thank you for your attention. So for the data, script, and algorithm that I presented to you today are available in GitHub, and also you can just scan this and then you can go to my GitHub if you want to test it. Thank you. If you have any questions, I can give to Erin.
Thank you so much, Mohammed. That was, really quite interesting. And I think for our COMET audience, who are normally very focused on tectonics and on volcanic systems, I think having that refreshed view on some landslide processing is, really great. I'll encourage anyone who is here with us just now to pop your questions in the Q&A box, and Ben and I will get to them. But while we wait on that, I thought we could kind of reflect on your presentation and probably ask a few questions. So I really liked the concept of you saying each pixel has a story to tell, and I think that will hit home quite a lot, because when we think about each pixel and its time series and then how that relates to other pixels spatially, when we think about those pixels in conjunction with each other, we can begin to understand those hazard drivers in space and time. And that's a lot, and very much what your research is about. When you're talking about these kind of pixel-based CCDCs or harmonic modeling, you're applying that. You spoke about landslides specifically today, and things like growing seasons and NDVI. How do you see this advancing into other areas like volcanics or like other types of hazards? Where do you see that moving?
Yeah, that's a good question, Sarah. Thanks for the question. So basically, like I mentioned before, that if we are dealing with time series, we are dealing with the natures. So every hazards, for example, they have their own time or they have their own patterns. Let's say now I'm talking about landslides. Landslides, usually we have these kind of patterns. Just back to here, we have these patterns, abrupt change from, if we have in y-axis is vegetation index, and this is the time. So usually the vegetations will drop, right? Something like that. So we are looking for something like that, especially in this case. That's why I'm applying some technique to isolate the NDVI drops, something like that. However, if you are dealing with the volcanic eruptions, let's say, we are not looking for something that suddenly drop in, maybe in the highly vegetated area is similar. We have a drop in NDVI, but if you are dealing with the volcanic eruptions, it's better to have sensitive bands. Like sensitive bands in volcanic eruptions, we can do with the thermal, or we can go to shortwave infrared, let's say. So if we talk about shortwave infrared, usually in the volcanic areas, you have a change that if previously like this, and then suddenly spike, right? And the interesting things, unlike in the landslide, you have NDVI like that, and then you have drop, and then it takes time to have a recovery. So maybe this will stay like segment 1, segment 2, right? However, in the volcanic eruptions, if you're dealing with the temperature, let's say you have segment 1, and then you have segment 2, maybe this is increasing in temperature. However, the segment 2 will not long last. Volcanic eruptions can be, after you have a cooling, it's become, for example, lava flow, it's become basalt, the temperature will be dropped. And then maybe you have a segment 3 in here. It's not completely dropped to the base temperature, but maybe it's quite higher. But you have maybe multiple segments in here. So in these things, we need to know, we need to apply, or we need to have a previous knowledge in the time series, let's say, how the behaviors of certain volcanoes or certain eruptions with the certain bands. So if we understand this, we can just decide, okay, well, we only want to find the segment 2. It means this is when the lava coming up. But segment 3, this is when the lava already cooling down, and this is completely cooling. So might be that's the things that I'm thinking about. Does that answer your questions?
Yeah, it does. I think the integration of various different data sources to do dense time series analysis is really interesting, of how we can integrate our optical bands and our shortwave infrared with things like INSAR, and then in turn thermal. And again, back to that, each pixel has a story, and build that picture up based on these pixels. I also think it's really interesting how you're looking to advance this, and think about the various different resolutions that come with those pixels. You had mentioned Planet and Landsat and Sentinel, obviously. Do you see a benefit, or do the results differ depending on that resolution of things like landslide inventories or some of the other hazards that you're looking at? Is that pixel resolution quite a key component?
Yeah. So again, it depends on our aim. For example, if our aim is only want to see the locations, let's say, we don't want to have a really have a good delineations. Let's say we only want to have an overview of the area impacted by some hazard like landslides or volcanic eruptions. Of course, the resolution, it doesn't matter. We can use the freely available data sets like a Landsat or Sentinels, because we only want to see the overview, the locations. And then also, of course, we want to have a time in the every pixels. However, if your aim is to have a completely delineations, if you want to delineate lava flows, let's say lava flow, pyroclastic flow, and then you want to have inventories of that things, of course, you need to go to the very high as possible for the spatial resolutions. And for the temporal, I think for the temporal, it's better, especially in CCDCs, or if we talk in generals in the time series, the more temporal resolutions, it's better. The better is this, because like, as you can see, this is Landsat. Landsat is every 16 days. Every 16 days, it means the next data set 16 days later, 16 days later. Although we have dense like this, but you know, in every point, the difference is 16 days. We're still missing in between, right? So if we can integrate, like I mentioned before, if we have harmonized Landsat and Sentinel to, even we can harmonize again with maybe with Asters, so we can make the data as dense as possible. So that's might be give us an advantage. Again, let's say if you're dealing with the volcanic eruptions, sometimes volcanic eruptions you have only short periods, it's less than 16 days. So if the distance between data sets is 16 days, it means we miss in between here. So that's the idea. If we have the data sets, so we can combine all the data sets together, so harmonize together, so we can just fill it gap in between, so we can make it denser time series in this case.
No, that's perfect. I think that really clarifies it for me. I'm not sure if anyone else has any questions. We'll give it a minute or so. But yeah, just again, thank you for this really quite interesting presentation. I hope that it's given a few of our COMET members maybe a different perspective, maybe a different type of hazard that they're looking at, or even just a greater insight into temporal segmentation that you spoke about. We very much appreciate it. Ben, have you got any questions?
Yeah, I had one actually on some of the results you showed on the sort of, was it the slope sectors, I think it was you said? Looking at the areas of the two methods. And I think the first one you showed had a good correlation, but the slope was at about
This
0.5.
This one?
Yes. Yeah,
this
perfect.
one. Yeah.
Which one was it? Yes. Or it might have been actually one of the earlier ones. I think it was the first plot you showed. Sorry, I couldn't. I meant to write down what slide it was on.
Yeah.
But anyway, in some of them you had a good correlation, but the agreement between the two is different. Like your landslide method had about half the area than the reference landslide area, whereas some of the later plots you showed, the correlation was quite bad, but they were getting the same sort of values. So I was wondering, what do you think the difference is in those two situations?
So yeah, the thing is we often also miss I mean the reference data, as you can see, especially in the northern sides here. In the northern side, this is our proposed method, and then in the reference method, they kind of missing here. It doesn't mean they're missing, but their area is only limited until these things. And also, we also have overestimate some of the landslide in this area. So this is related to this is not really a landslide, although in reference, they don't have landslides here, but there's a change in these areas, but not related to, I would say landslide, but this is still change due to the mining activities here. So we detect also mining activities, we have NDVI drop, sudden NDVI drops, and then the drop is just constants like this, but it doesn't mean this is landslide. Although we already have filtering the slope, the waters, but we still detecting non-landslides. But that's, part of the remote sensing, although we already filtered some things. But this one, because it's the characteristic similar with the landslides, mining activities, you do the mining activities in the high slopes, so it means vegetation loss. So the computers detected as landslide. So that's one of the problems also we have in this kind of big area. This is quite big. I think I forgot how many kilometers square. So as you can see, this is the scale, 120 kilometers from here to here. Mm. So that's quite a huge area for the landslides.
I guess similar to that, then, do you have any issues with an incomplete inventory?
Yeah.
Yeah.
Yes.
I think most landslide experts would say the same. I'm aware Lorenzo Neva was here, but I think he's popped off now. But many of the landslide experts we work with at BGS, the one thing they will ask is, do you have that capability of having that inventory that spans time and space? And it's often the largest component of making things difficult, essentially. So I really appreciate Ben's question there, because it kind of made us think, well, actually not everyone maybe knows these sorts of things. And actually, when we're detecting change, as Mohammed had said, that we're detecting that change from space, we then have to still make sure that we understand what's actually happening on the surface. And without that context, that change can be misinterpreted, or it can cause correlation or not causation and whatnot. So I think that's really important. I don't think we've got any questions. It seems everyone's been a bit quiet today, but that's fine. So we'll probably leave it here. Thank you very, very much, Dr. Mohammed. And to our COMET viewers today, we will see you soon at the annual meeting. If not, stay tuned for our next webinar. But thank you all very much for attending, and we'll see you soon.
Thank you. Thank you very much, Erin and Ben. And thank you very much, all of the audience. See you soon.